All right, so welcome to Math 372 complex analysis, except it's not 372. What is it? Oh, I didn't join the audio. Oh, thank you. Oh, wait, no, I think that's fine. I'm not joining the audio on the computer in here, but the audio is on my computer here. But please, if you do see things that look like they might be not working well technologically, speak up. So this used to be 372, it's now 383. I'm just using the old, slides from there have not been that many major changes in the introduction to complex analysis, in the past 2 or 3 years. So I've been recording all of my lectures for 6 years. So when the pandemic hit, it took me about 20 seconds to tell my Calc 3 students, okay, we're now switching to 2014. So this gives us a lot of interesting opportunities for how we want to treat this semester. Given that we have all of the lectures recorded, this gives us the ability to restructure and actually spend more of class time discussing applications, discussing other topics. If people want to investigate various projects, I am happy to adjust things. If you are interested in graduate school, this is a class that is going to be run at a graduate level. This is one of the reasons why it's a 300 level class and not a 400 level class. This is why we moved it up to 383 from 372. So when you're applying to graduate schools, I'm happy to write a letter of recommendation and talk about how you have demonstrated that you can handle work at a graduate level. We just can't call it a graduate level class in terms of the mechanics. All right, so what I want to do today is talk a little bit about the course mechanics. The most exciting part of any course, is of course discussing how we're going to handle all the stuff, and then talk a little bit about some of the basics. What are the prereqs for this course? Real analysis. So you are supposed to have taken real analysis. What we really need from real analysis is sequences, series, convergence, and a little bit of point set topology. That's the most important stuff. Some of the more esoteric theorems we don't need as much, except for the beautiful Riemann mapping theorem, which depending on the mood you and I are in can take anywhere from 3 days to 2 weeks to just go through all the details. It's worth at least once in your career seeing a proof that is this technical to give you a sense of why you need stuff like this. When I was a college student, I wanted theorems proven in the greatest generality possible. When I got to graduate school, I realized I was wrong, and that of course all of my functions are infinitely differentiable with rapid decay. And then when you start to use the math to solve problems that you care about, you often have a lot more structure than the most general case. Now, it's nice to have the theorems as general as possible because you don't necessarily know what condition you'll be in. But for many applications, things are going to be very nice and we don't have to worry about all these technical cases. Right. So obviously, big part of the class is learning complex analysis. I want to emphasize the techniques of the subject and I want to emphasize asking the right questions. Complex analysis is very different than real analysis. So later today, I hope to go through at least 4 different examples of things that are completely different between the two subjects. And so your intuition in real analysis will often fail you in complex analysis. And the reason is, how many of you remember Math 151 multivariable calculus? How many of you took Math 151? You should have at least taken that or some equivalent of that if you're in a class like this. But we will see later that Green's theorem for multivariable calculus is essentially the key result in all of complex analysis. It's Green's theorem applied to a nice function. If you had your choice and you could integrate any function you want, what function would you choose to integrate? Your grade depends on getting the answer right. Be more specific. 0, right? Because if you choose the constant function, then you might need to know what is the length. If you choose the 0 function, it's pretty easy to give me what is the integral of the 0 function over any region. Just for definiteness, it is good. Yes, it's 0. Okay. So if you are integrating the 0 function, it's pretty easy. Green's theorem basically gives you a line integral is the same as an area integral. And if one of the two expressions is 0, then the other one has to be 0. And so if you have a function where you have your dq dx minus dp dy equals 0, then the integral is just trivially 0. And complex analysis, it turns out that complex differentiable functions satisfy that equation being 0, satisfy an analog of that being 0, which make a lot of integrals easy. We're going to see that we can convert a lot of integration to basic algebra, to finding the negative first term in a Taylor series expansion. It is much easier to do algebra like that than to do integration. So what do you learn in Calc 2? I'm sorry? Okay, what should you learn in a good Calculus 2 class? When you leave Calculus 2, what do you feel like you can do now? You feel like you can integrate. You can't. I can't integrate either. Professor Lepp can't integrate. No one can integrate well. We have to work damn hard to give you functions that you can integrate. It is a lot of work to come up with functions that integrate and have nice closed form expansions. If I were to just randomly combine functions, odds are highly, highly, highly unlikely that you would have a nice closed form solution. What about differentiation? Is differentiation easy or hard? Easy. I can't stump you as much as I try. Just rattle it away. Use the product rule, the quotient rule, the composition rule. And whatever I give you, you can find the derivative. You may not enjoy it. It may take a long time, but I can't give you something you can't differentiate in closed form. Integration is completely the opposite. Integration is extremely hard. And so one of the great things about complex analysis is we convert a lot of integration to very simple algebra. And a lot of integrals that were very hard to solve before, we now get very easily. And we often can parameterize them, and we can solve whole families of integrals very easily. So out of curiosity, how many of you are at least considering graduate school in some subject? Okay. So a good number of you are considering graduate school. How many of you are not considering graduate school and want to go off into industry? Okay. Anybody a senior here who will be applying for jobs? Okay, so you are both taking an extra class right now if you are applying for jobs. Applying for jobs is a 5th class. So homework, deadlines, everything like that is always flexible as long as you give me at least a day's notice. If it's less than a day's notice, it has to be something truly shocking that you could not have anticipated. Such as, I've got tickets to the luxury box at Fenway Park, and I would really like you to come so you can help me talk. Something along that lines would be acceptable. In general, you should be able to plan accordingly so that if something happens, you're not putting things off to the last minute. I'm happy to do practice interviews. I'm happy to talk to people about various graduate schools and whatnot. And again, if you have any deadlines, sporting events, whatever, plays, let me know. Happy to adjust things. All right, we will see a lot of applications of material in earlier classes. How many of you have done probability? Excellent. How many of you have seen the central limit theorem? How many of you raised your hand to only one of those questions? So did you take a probability class and not see the central limit theorem, or did you see the central limit theorem without seeing probability, without taking probability? Okay, but you've seen the central limit. Okay. You should not take a probability class without seeing the central limit theorem. Certain words highlight how much we care about them. You don't use words like central or fundamental lightly. There are not that many fundamental theorems that we have. Okay. One option for this class is to actually mostly prove the central limit theorem. Normally in a first class in probability, we state what the central limit theorem is and we prove some special cases. But why is it true? And not just why is it true, but how quickly does it converge? Any stats majors here? Sometimes in stats, we often talk about how many data points do you need before you can be confident that something becomes normally distributed. Anybody know roughly how many data points do you need? Yeah, around 30. And it's one of these things that's like Moses coming down from Mount Sinai that just passed down from class. Around 30, you should be fine. Well, how do you estimate roughly how many points we need before we have good convergence to the Gaussian? And so we can talk about stuff like that. We have a lot of flexibility in terms of what we do with the material. And so depending on what your interests are, I'm happy to adjust. If people want to break up into small groups, learn things and present it to the class, absolutely fine. Again, we have a lot of flexibility with how we do things. And so just some set of problems. So I was trained as a number theorist. I still do a lot of number theory. So much of complex analysis was developed because people wanted to study the primes. Can somebody define the primes for me? Yes.
On numbers, like the only factors are one.
So do people agree with that definition? Primes are numbers such that their only factors are one in themselves. Okay, how would you modify that? It's close. You have to exclude one. We do not want one to be a prime because if one is a prime, we lose one of our fundamental theorems, the fundamental theorem of arithmetic. Yeah, that's a good question. Depending on who you count, you could actually count a negative number as a prime. But I'm quite happy to say, let's just consider positive numbers because they differ by a unit. The unit is -1. So let's say positive numbers, at least two factors. It seems like complex analysis should not necessarily be a useful tool to study primes because primes are integers. These are not just real numbers, they're integers. Why should we be going to the complex plane? So one of the great quotes about the subject is sometimes the shortest path between two proofs about real numbers is through the complex plane. It shouldn't be surprising because complex analysis is so powerful, we're throwing an elephant gun at the problems. And it turns out a lot of complex analysis was developed by people trying to understand how many primes are there up to a given level. And the proofs all revolved around advancing our knowledge of complex analysis. And so there is a function called the Riemann zeta function, which if you have not seen, you will see by the end of the semester, which encodes information about the primes. Any physicists here, or potential physicists? All right, so what is the Heisenberg uncertainty principle? You cannot know position and momentum arbitrarily well simultaneously. That the product of your uncertainty in the two is greater than or equal to Planck's constant, or Planck's constant divided by 2 pi, depending on what units you want to use. It turns out that the uncertainty principle is actually a statement about a function and its Fourier transform. The Fourier transform is integrating your function against e to the -2 pi I xy. And so we will see in the semester, people want how to view the Heisenberg uncertainty principle as a mathematical theorem about a function and its Fourier transform. The physics content is that this actually corresponds to position and momentum. But the uncertainty principle is really a result about a function and its Fourier transform. Another great thing we'll see in the class in terms of applications is the method of stationary phase. So what is n factorial? N factorial is n times n minus 1 times n minus 2 all the way down to 1. What does n factorial represent? Number of permutations of n objects, be a little bit more specific, where order matters. So if you want to estimate n factorial, there's a couple of ways to estimate it. Integral test from calculus is a great way to estimate it. We will develop the method of stationary phase, which does a great job of investigating quantities like this. And the way we do this is we actually come up with a real valued function that agrees with n factorial at the integers, but it interpolates it. If you've taken probability, you've actually seen the interpolation, although it may not have been emphasized. When you look at the normal distribution, anybody remember the normalization for the Gaussian, for the standard normal? Yes, 1/√2 pi. It turns out that the square root of pi is basically -1/2 factorial. So you might be a little bit concerned about what is -1/2 factorial because it's a negative number and it's not even an integer. But it turns out we are very good at taking things that are well defined and generalizing them. Anybody remember the geometric series formula? Good, 1 plus x squared plus x cubed plus ... equals 1/1 minus x. Is everybody happy with that? Thank you. If x is, got to be more specific, x less than 1 is not quite right. Because I could take x equals -5. -5 is less than 1. So absolute value of x is less than 1. What if I take x equals 2? 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 and so on, so on, so on. What would that equal? it diverges to infinity. Or if I use the geometric series formula without really worrying about it, I put on my physics hat or maybe even better my engineering hat, I get -1. And so you would say the sum of all the powers of 2, it blows off past positive infinity, comes in from -infinity, and almost makes it back to 0 and stops just a little bit before. It turns out you can actually make sense of the fact that the sum of the powers of 2 is -1. If you know anything about p-adic analysis, there are ways to talk about the p-adic, and this actually makes sense. So there's a lot of interesting ways you can take some of these functions that you've seen and extend them. All right, so again, my main experiences are zeros of L functions and eigenvalues of random matrix ensembles. These have modeled so many different things. There is so much complex analysis and stuff like that. I see, several people here who have done small with me, who have worked on problems related to this, where frequently complex analysis comes in. All right, so course mechanics. So we are going to move at a fast pace. You are responsible for reading the material before class and coming to class prepared. So I will assume, unless you tell me otherwise, that you are prepared, and you will have 5% of your grade like that. Homework is 15%, midterm is 40%, final is 40%. You can do a project for up to 10% of your grade. If you want to negotiate for more than 10%, I'm open to discussion. And again, this is your chance to guide and adjust your education a little bit. So there's a lot of different projects you can look at. I am working with a colleague right now who has, interestingly, the same name as me, born same year, same city, but is not me, same thesis advisor. And we are working on a book on L functions and sphere packing. And so if people are interested in working on that, that would absolutely be something acceptable for this. If you have not seen Green's theorem, I have a link to, I hope, the correct link to a lecture I gave years ago in Calc 3, Green's theorem in a day. So it's a 50-minute lecture that just very quickly goes through what is Green's theorem, how to use it to do these contour integrals. If you've done Math 150, depending on who you had as your teacher, you may not have seen Green's theorem because it is not required for the course. When I teach it, I do have at least a day on Green's theorem. I feel that if I don't do that, if I die and I'm, on the borderline of do I make it to mathematical heaven, I need to be able to say that all of my students have seen Green's theorem above a certain level. It is an absolutely brilliant, beautiful theorem. It generalizes wonderfully to higher dimensions. And we will be looking at complex analog of it. You do not need to know the real variable analog, but if you've seen it, it's very helpful. All right, so again, just on the mechanics side, my webpage uses state-of-the-art 1990s technology, directly coded in HTML. The advantage of this is I can make this stuff freely available to anyone in the world. You don't have to go on through Glow or any other computer software. When I moved from school to school, which happened a lot when you're younger, I could just move all the files with me. Homework might be posted through Glow, it might be on my homepage. I have to talk to the grader and see what the grader wants to do for this class. There will be lots of handouts, comments, and whatnot on the course homepage, a lot of reference material. So just if you explore it, you should be able to find some good stuff. Prepare for class. I will probably say this multiple times. The more you do beforehand, the more you're going to get out of the lectures. I want to use the lectures efficiently. I don't want to spend lecture time saying, and this is the definition of the rational numbers, this is the definition of the real numbers, this is the definition of complex norm. If you can do stuff like that at home and then let me know what you found confusing, it frees up class time to be more productive. And so we only have so many hours to meet. We don't have as long of a semester at other places. And so the better allocation we have of time, the more interesting material we'll be able to see. All right. And then again, if there are topics you want to see, let me know. I'm happy to try to work them into the course. All right. And then some advice from my brother, party less than the person sitting next to you. Take advantage of office hours and mentoring. You are at a school where the professors actually want to be with students. Not everyone is at such a school. I was at an institution where a professor had office hours. It was either 8 or 8:30 a.m. the day after homework was due. What message does that send the students? Don't come. The students got the message. So you are at a place where the professors are actually happy to. We have celebrations as faculty. We got to teach again. because it's been so long since we've gotten to teach. We're actually excited about this. Take advantage. I tell my advisees, your goal, one of your objectives every semester is to get to know at least one professor well. And that way, if you fail half the time, you will still graduate with 3 or 4 people who know you well enough to write letters of recommendation. Get to know, it doesn't have to be me. I'm happy for it to be me. It doesn't have to be me, but you'll get to know professors. Come to office hours, get to know people. I am a huge fan, as some of you know, of the walking office hours, especially given that we now have to wear masks indoors. Happy to go for a walk, take people out for lunch or ice cream or coffee, whatever, let me know. Happy to do it in small groups or large groups. When you make comments in class, please email me after class and say, Professor Miller, I made the following comments. Even if you think the comment is trivial, please email me. It helps me get to know you, gives me a chance to talk to you a little bit more about various things. And then when I'm writing letters of recommendation, it gives me the opportunity to be detailed, because I keep sheets of everything. And this way I can be a little bit more specific when I write this. Last piece of advice from my brother is learn to manage your time. No one else wants to do this. Okay, so really important to make sure you get things done on time. If you receive an email, you should respond to the email within a day, even if it's just to say, I'm too busy. If you're not going to be able to respond to emails, put up a vacation message. If you know you have a big homework assignment due on Friday, start doing a little bit of work on it throughout the week, so you're not leaving everything to the last minute. How many people have friends in the communities that they hang out with? When I was in college, there was a disconnect where they didn't understand why we couldn't tell them when we would be free. You're just doing your homework. Don't you know when you'll be done? No, it depends when we're divinely inspired and figure out how to look at the damn problem. Whereas for them, we said, well, you know how many pages you can read in an hour, you know how many pages there are. If you can't do the division, I'll do it for you. And I can estimate when you will be free. Whereas for us in a math class or a physics class, we would have no idea sometimes how long it would take us to do a couple of problems. So some of the problems you might look at and you might say, oh yeah, this one looks like a straightforward calculation. Another one's, oh my God. So I strongly encourage you to work in groups. Just put on your homework that you've worked with people, more the merrier. It's to your own best interest to make sure that you understand things. All right. And then, as I said, I am happy to do practice interviews. So if you're going to be on the job market, I am happy to represent a company and interview you. Happy to give people some general advice and feedback on how to handle interviews, how to work with CVs and stuff. Happy to adjust deadlines if you have things that are coming up, so long as you can give me some preliminary announcements. God forbid a complete tragedy happens, I will adjust deadlines with less than 24 hours, but most of the time your things should be known in enough advance, so it's not going to be an issue. All right, any questions on the mechanics? Yes. Yes. They will be available. So in fact, all of the lectures from the previous iteration are already available. And so sometimes I actually watch the lectures beforehand, sometimes I don't. It's nice, last semester I was teaching 2 sections of Calc 3, and it's sometimes boring to give the same lecture back to back. Sometimes it's more fun not to look at the notes and just see what are we doing and just try to do it live. Sometimes with very long technical calculations, it's not bad to have some rough idea of, so what was the key insight again? But everything is online. So there will be lots of lectures that are very similar from year to year, but we have the option now, we're coming out of the pandemic. I don't know if I can still say we're coming out of the pandemic. We are adjusting to being in a pandemic mind state. And this gives us the opportunity to rethink how we are doing things. And so I accelerated my daughter last year in math. She was in 6th grade, but because the schools were remote, she actually took Algebra 1 with the 8th graders at the middle high school because there was no problem for her to Zoom in. And so there's more opportunities now. And we really want to think, what we've been doing for all of these millennia, is this the best way to go? When you look at this beautiful new classroom, what do you notice? That is maybe a little old-fashioned in the 21st century. Yeah, we still have blackboards. You're with the math department, math stats. Not sure stats might not agree with this, but you're with the math department. We have blog posts on chalk. And so we still have blackboards. My kids have better technology in terms of the smart boards in their schools than we have here. And so it's worth rethinking how we're doing things. One of the reasons I'm trying to do things on the portable screen is this allows me to have notes for it just saved. I can of course stream and record things from the board, but if I do it like this, I can just put it in a PowerPoint presentation and then just post the slides after class. And we'll get a sense as to, is that better or not? One of the disadvantages of doing that is it limits the real estate that you get to see to one screen. So one of the advantages of not doing something like this is I can fill up math on multiple screens. If you tune out for a second, I was a student, it happens. You can then just quickly look and see, oh, what were we doing again? Ah, got it. Whereas when you're doing a PowerPoint Beamer presentation, when you're doing something like that, it really constrains what you can see. And so this is something I want you to think about in terms of how you want the semester to go. Other questions or comments? Yes.
Will we have just one midterm?
We will have just one midterm. And then cell phone policy is if your cell phone goes off during class, there's a pop quiz for everybody the next class. If you are expecting an important call, then just let me know. I'm about to get a call as to an interview and I have to respond immediately. Don't have your cell phone on silent. If my phone goes off, then there's one in the bank for you. And so my phone number is on the homepage, 617-835-3982. You're welcome to have one of your friends try to call me during class to see if I have left my phone on. Or instead of a quiz, the other option is somebody has to bring donuts or snacks for everyone. So I'll let you think about what you want as the class policy. I'm not sure if we're allowed to actually, I don't think you can eat, and you would have to take the food for later. Any other mechanics questions? Okay, so what I want to do now, right. So hopefully this is projecting. Okay, good. So can someone tell me the definition of the derivative? Say f prime of x. Sure, the function of real variable.
So the limit h equals 0.
Good. So this is a really good definition. Should this definition extend easily to a complex number? Yeah, it seems like this should actually be a really good definition. It should extend without any trouble to a complex number. How many, I'll risk asking this question. How many of you remember multivariable calculus? What is the definition of the derivative for multivariable calculus? What does it mean for a function to be differentiable?
Same idea, but the limit has to be the same and exist for every function.
So how would we define the derivative? So you'll be looking at the partial derivatives. So the existence of the partial derivatives is not enough to imply that the function is differentiable. So you need more than just the partial derivatives exist. There's lots of ways of writing the derivative. Sometimes we might do the point x naught. Oops, sorry. So sometimes you might do things at the point x naught. And so f prime at x naught would be just going like this. How could we rewrite this? Well, another nice way of writing this is we want the limit as x goes to x naught of f of x minus f of x naught over x minus x naught. Is that an acceptable equivalent definition of the derivative? I'm just having x be x naught plus h. So it's not so bad to write that. So we can convert this. So we want the limit as h goes to 0 of f of x minus f of x naught I'll make sure that you can see that there's a minus sign, minus f prime of x naught, x minus x naught, over x minus x naught equals 0. So what I've done is I've taken, well, f prime of x naught equals this. Let me move f prime over. Since that has no x dependence, I can just bring it inside the limit, and I've just multiplied by 1, x minus x naught over x minus x naught. And when you take the limit, x is never x naught, so this is allowed. So my professor, did I make a mistake? Oh, sorry. It's not h, what should it be? Goes to x, x goes to x naught. Thank you. Thank you. And this, which the second one should be f of x minus f of x naught. Okay. So once we've fixed all the typos, this is essentially the same as what we had before. I've just now moved things over. It's an equivalent definition. What this is saying is the tangent line does well. Tangent line does well. And that's really what we have over here. This is the tangent line approximation. And so for a function to be differentiable, what you're saying is if you approximate it by a straight line locally, it does such a good job that when you divide it by how much you're moving, x minus x naught, it's doing so well that even when you divide it by that, it goes to 0. If your function is nice, it'll look like maybe x minus x naught squared. But it doesn't have to be that high. And so in multivariable calculus, the natural generalization is the limit as the vector x goes to the vector x naught. I like to put arrows to remind myself that it's a vector of f of x minus f of x naught minus the gradient of f at x naught, x minus x naught, divided by the length of x minus x naught. And again, I'm using double lines to indicate that it's the length of a vector. Here, these are real numbers, so I can just use a single value. I'm sorry? Oh. On back order. It's part of the global supply chain issues. This is the correct generalization. It's now saying that the tangent plane or the tangent hyperplane does a really good job. And that's what works well. So it's not enough for the partial derivatives to do a good job. You need to have all the different approximations. All right. Any questions about the definition of the derivative? Yes.
When you say like it's not enough for the partial derivatives, does do you mean?
I can give you a function where df dx and df dy both exist, but the function is not differentiable. And it matters what paths you take. So let's talk a little bit about paths. And so when I first started teaching at Williams, my kids were young, they were in the Children's Center, and I had them and their friends make individualized pictures for each of my students. Anybody ever see the Karate Kid movies? So in one of the movies, you learn the secret of Miyagi karate. It's a little doll that goes back and forth like this. If you do things in the real line, how many ways can you approach the point x naught? How many paths do we have really to get to x naught? We essentially have two, right? You come from the left or you come from the right. If I tell you the limit exists, I'm really not giving you a tremendous wealth of information. Now, this is the real case. Let's look at the complex case. And I give you some point x naught. How can you approach it? I could approach it along straight lines. I could approach it along a parabola. I could approach it along some kind of spiral. Or I could have some kind of strange, God-forsaken mess like that. All of those limits have to be the same. So when you say the limit exists in 2 dimensions and higher, it is a serious statement. And so just having the limits exist in certain directions is no longer enough. This is the secret to complex analysis and multivariable calculus. The fact that we have to be able to handle limits like that. And they are much harder to handle. So what we don't want to do is we don't want to calculate that the limit exists for every single path, because there's infinitely many paths to look at. We need to find ways to say, this is enough to show that no matter what path you take, it's going to converge. Okay, so the question then becomes, what should the definition be for complex? So complex derivative, we will use f prime of z naught is the limit as h goes to 0 of f of z naught plus h minus f of z naught over h. And so that is a really good definition. So can somebody give me a function that you think might be complex differentiable? Okay, let's be a little bit nicer to me first and work my way up. Constant, right? So we could try, f of z is some constant. And what would that give us? That will give us the limit as h goes to 0 of c minus c over h. That's just the limit as h goes to 0 of 0, that's 0. And so just as in the real case, you would get the derivative of a constant to 0. What should we try next? Polynomial, any specific polynomial near and dear to you? Really, you're going to force me to do x squared? X. Except you don't want to give me x. Z, right? We want to use notation that is easy to just quickly look at. And so we will try to use z and w for real plus imaginary. So if we wanted to take f of z equals z, then that would give us the limit as z goes to 0, I'm sorry, as h goes to 0. So limit as h goes to 0 of z naught plus h minus z naught over h, which is the limit as h goes to 0 of h over h, which is just 1. So you get the same derivative as before. As a nice exercise, you can then show z squared, z cubed, and in general, z to any positive integer n is differentiable. There's lots of ways to do that. I will not give you any hints as to which way I might prefer, but as a nice exercise, prove that z to the n is differentiable for any n. You might remember complex conjugation. So if z equals x plus iy, then z bar is x minus iy, where I either is or am, depending on how you like to do English, the square root of -1. And it turns out that this function is not complex differentiable. So if we try f of z equals z bar, we would get the limit as h goes to 0 of z naught plus h bar minus z naught bar divided by h, which is the limit as h goes to 0 of h bar divided by h. And so depending on what we choose for h, we're going to get different limits. If I choose h to be real, what's this limit going to be? 1. So this limit equals 1 if h is real. What if h is I times a real number? What if h is pure imaginary? Then it would be -1. So it's -1 if h is an I times r. So it's not differentiable. So not every function is complex differentiable. So essentially the only functions that are complex differentiable, it's x plus iy that occurs, not x minus iy. So let's look at z as x plus iy and z bar is x minus iy. What's z plus z bar over 2? It's x. And z minus z bar over 2 is is IY. So I don't want to do Z minus Z bar over 2. What do I want to do? Over 2I. If I do 2I, now I get Y. So what this tells us is I can go back and forth between the coordinates Z, Z bar and the coordinates X and Y. So if I give you any function of X and Y, I can rewrite it as a function of Z and Z bar. If you're a function of Z, that means X and Y only occur in the form X plus IY. They don't occur in any other way. And it's going to be those functions which will be complex differentiable. Okay. Any questions on what we've done up till now?
Function that you have for
Yes.
what is that?
It would well, so f of z equals c just means no matter what input, I give you the same output. So it's basically
real function that would be a y, right? If we're talking about a complex function, what is that?
so that would be your y equals c, that would be like a straight line. This would be, a plane of a certain height.
Would be a function.
No matter what point you have, I'm always going up c units.
So graphing a complex function.
We can't graph complex functions because a complex function has 2 inputs. And if it's a complex function to a complex number, it has 2 outputs. It's 4 dimensions. So what you can do is you can play games. One game is you plot the absolute value of the complex function. And that you can then do in 3-dimensional space. Or what you can do is you can plot it, but you can have not just the height, but the color indicating maybe the angle. If you're writing it as r e to the I theta. But unfortunately, we can't plot complex functions. And so we lose a lot of the intuition of just being able to look at things. All right, so what I want to end with is the differences between real versus complex. So here's the property. Real differentiable, complex differentiable. And the question is going to be, is the answer yes or no? So I'm going to assume function, I have a differentiable function. So f, g, dot, 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 are differentiable functions. F is infinitely differentiable. True or false for real valued functions? False. Yes. Completely different. You can have a real valued function which is differentiable once or twice, and that's it. But in complex analysis, once you are differentiable, once you are infinitely differentiable. That's nice. Can anybody give me a function that's differentiable once, but not maybe twice or 3 times? Anybody remember the counterexample? Absolute value of x is not differentiable. I'm sorry? Well, but if it's piecewise, it's not going to be differentiable.
Integral through x, that's the way.
All right, so you could try something with integral. There's a nice straightforward. Log of x is still differentiable except at one point. The typical example people often use is something like x squared sine of 1 over x. Because now as x goes to 0, this is still going to be continuous. It's going to be differentiable. But it won't be differentiable multiple times. Maybe I have to do x cubed to be safe. I don't know. Something like that. So the next property, function equals the Taylor series. So is that true or false for real valued functions? False. So that's a no. And complex? Yeah. At this point, you should be able to figure out what the answers are. So for example, if I give you the function e to the negative 1 over x squared, all of the derivatives of this function at 0 are 0. This is a great application of L'Hopital's rule. So this function is infinitely differentiable. It has tremendous decay. And if you take x equals 1 over 100, then you get e to the negative 100 squared. That's small. E to the negative 1 over a million is now e to the negative million squared. All of the derivatives of this function are 0. So if you looked at its Taylor series is identically 0. This is an aw shit moment. Taylor series are not unique. If I give you the function e to the x, you're thinking 1 plus x squared over 2 factorial plus da da da. So if I give you 1 plus x squared over 2 factorial and so on, what function am I thinking of? I might be thinking of e to the x, or I might be thinking of e to the x plus 1,701 copies of e to the negative 1 over x squared. And they would have the same Taylor series. So the Taylor series does not uniquely determine the function. Can be bounded and not constant. So can you give me a differentiable function which is bounded but not constant? That's real value. Sine, cosine, 1 over 1 plus x squared. So the answer is yes. What's the answer for complex? Yep. So it goes the other way. I didn't want to have everything being yes and no. So you can have a complex valued function that's constant, that's bounded, but if it's defined for all complex numbers, the entire complex plane, it has to be the constant function. The last one, I'll skip the last one. I'll leave it. This is enough stuff going on. So to just put this at a really high level as to what's going on and what's the difference, to use language which may not be appropriate, this is how you should view real analysis and complex analysis. Real analysis is the democratic subject. Real analysis will let any function in, come on in, the more the merrier, you're welcome, we're happy to consider you, we're happy to study you. Complex analysis is the elite country club that has extremely strict requirements over which functions it lets come in. It's not surprising that complex functions that are differentiable have a lot more properties, because if you look back, it's a much more stringent condition. And what's really going on is we are only looking at functions that we can apply Green's theorem to, where we're integrating 0. And that's going to have a tremendous number of applications and consequences. And this is why complex analysis is so different. Because a function that's complex differentiable, it's not just a simple generalization of a real differentiable function. This is why the subject is completely different. And then you know what subject is going to have very much different behavior than complex functions of one variable? Yes. Complex functions of 2 variables. Exactly. And so the geometry completely changes things again. All right, so this is a good place to stop. If anybody wants to chat for a little bit afterwards, I am happy to hang around for a little bit.